Okay, hello there. Welcome to another week of Science and Technology Q&A for kids and others. I'm a little busy today because I'm getting ready for a grand centenary tomorrow. No, not tomorrow, Monday actually, of the invention of things called combinators, which were an early precursor of what we now know of as universal computation. Not well known, but very important in the historical development of what we now know of as the idea of computation. Anyway, I'm trying to get ready some material for an event for that day. But let's start off. We have some questions left over from last time. We have one from Shuri. Why do people refer to the internet as the World Wide Web? What's the relationship between networks and websites and all those kinds of things? All right, we can try and talk about that. So there's really several layers of what the internet and the web and so on are. In the end, the internet is a network that connects a whole bunch of computers together. One of the things that a lot of those computers do is to provide websites. And you connect to websites through the internet. But the web itself is that connection of websites, not the underlying connections between computers. So we can talk a little bit about how the web works, how the internet works, and so on. So you'll notice when you type in the address for a website, it usually starts HTTP or HTTPS, and then it has a bunch of other stuff in it. What that HTTP stands for, it says it stands for Hypertext Transfer Protocol, transport, I'm not sure, protocol. And that is telling, that is a way of saying this piece of information that's available from this computer is going to be transported in this form so that it can be read by programs that can read that format. And so for HTTP, the main kind of program that reads that format is a web browser. So a web browser, if you look at what is coming from to your computer when you connect to a website, you'll see all kinds of data. That data is in the format. It's being transported in HTTP form, and most of the content is in HTML, which is the standard basic language of web pages. And then what your web browser does is to take that data that's being transported in HTTP form and show it as a website on your computer. But so what's happening underneath is there's what has to happen is that the data has to be transferred. That's the job of the internet. The web is the parts of that data that are in a form that can be consumed by things like web browsers. So for example, there are other prefixes other than HTTP. There are other prefixes that you can see there that are intended for programs other than web browsers. For example, another one is FTP. That was an older type of way of transferring data over the internet. FTP stands for File Transfer Protocol, just a way of taking a whole file and sending it over the internet. There are other things. For example, we have one, WSTP. It's a transfer protocol for symbolic expressions in Wolfram language. That's another thing that you could see in front of instead of HTTP as the thing describing what kind of data you're going to get from a computer if you connect to that place. Now, the thing that is the specification of where you're going, usually called a URL, is the thing that kind of tells your computer kind of where to look for information on the internet. Oh boy, this gets kind of complicated. So there are things called URLs. There are also things called URIs, which are a bit of a generalization of URLs. But let's talk a little bit about URLs and what they mean and how that all works and so on. And essentially what's happening is that URL that says something like, I don't know, www.wolfram.com, that URL is something that your computer can use to, that's a way to specify the computer that can deliver certain kinds of information to your computer. So I'm pausing a little bit because actually the whole story is really quite complicated. And that address could actually not just be one computer. It could be something which is where sort of the information associated with that address is delivered by multiple computers. All right, but let's start off with a little bit more of the basics of. Let's talk first of all about the internet, what it is, and a bit about how it works. So the internet is a big collection of computers, probably by now 1 billion of them, maybe even more. It grew out of a thing called the ARPANET that people like me used to use back in the 1970s, actually. The ARPANET was a connection in those times of like 256 computers. And in those days, you would refer to a computer on the ARPANET just by a number. Like my favorite computer was one called 236, which was a computer at MIT. And you would basically connect to the ARPANET, say what number of computer you wanted to get to, and then you would be able to start sending information to that computer, getting information back from that computer. One of the big innovations of the ARPANET, became the internet, was the question of sort of how the information was sent from you to that computer. And the idea was that there were multiple paths by which it could send. It would get sent. It would go from your computer to another computer, to another computer, to another computer, and eventually get to the computer you wanted to communicate with. And the idea was that even if one path, one route to get from you to the computer you wanted to get to was somehow broken, you could still, the system would automatically figure out another route which would allow you to get to the computer you wanted to get to, so that it made for a network that was wouldn't be able to be taken down by just one computer failing and so on. Now, the way of calculating what was the best route was kind of tricky, and still kind of tricky. There's a lot of kind of black magic associated with working out those best routes. There was a time long, long ago now when a computer, I think it was in Hawaii, really confused what was then the early internet, I think, by sort of broadcasting to the world, when you send data through me, the data will arrive in negative time. And so all the other computers said, well, that's a really great place to send our data through. So everybody started routing data through this computer in Hawaii. Needless to say, it got overloaded and the internet sort of went down. It was a long time ago. But that's the kind of problem that can happen when you're saying there are these multiple routes through the internet and you're trying to figure out which is the best one and so on. Okay, well, what happens today? Well, today, computers on the internet are specified by addresses, so-called IP addresses, and they would be things that the original version is IPv4, which has these 4 blocks of numbers. And so different companies and countries will get particular blocks assigned to them. So there are things like a Class A network says you're going to get everything that's after that first block of numbers. Class B network, everything after the second block of numbers. So for example, my company, Wolfram Research, we were very early on the internet, probably around 1987 or so, maybe 1986 even. And so we got assigned the Class B block 140.177. So everything after 140.177.10.20 or something, everything after 140.177, that's part of our section of the internet. It's kind of a funny thing because we were early to the internet, our block of internet space is bigger than some countries and so on. But that's just the way these things tend to work. But anyway, so every computer that's sort of exposed to the internet gets one of these addresses. The world kind of ran out of IPv4 addresses, so that's why IPv6 is really the thing that's coming in, and that has a longer address block. So more computers can be separately connected to the internet. So, okay, so you've got this IP address. And the question then is, what is the relationship between that IP address and the thing you type in, like wolfram.com, for example? Well, so what has to happen is something has to translate from you typing in wolfram.com to your computer somehow knowing that that means you're trying to send information or get information from some computer in the 140.177.whatever internet address. Okay, so first sort of complicated thing that happens is the so-called DNS lookup, which is how do you associate wolfram.com with 140.177 and so on. And so what happens is there are a whole collection of layers that do this, but actually there are two sort of things that have to happen. One is how do you associate wolfram.com with 140.177, et cetera? And second, how do you actually get from your computer to a computer that is serving, that is at the internet address and that's serving the content that comes from wolfram.com? What is the route that you will go? So there's this notion of, first of all, how does the DNS lookup work? How do you get the routing table that tells you what the right route is, and so on? And the way it's done is there's sort of layers of information. So for example, if you've been to wolfram.com recently, you might have cached, stored on your computer, the information of, oh, that's 140.177. whatever. But maybe you didn't go there recently. Well, then your computer won't know it, but a computer that your computer is connected to does know. And then a computer that computer is connected to does know. And eventually you kind of peel backwards. And for example, the .com top-level domain, you can ultimately look everything up that comes from the .com top-level domain through the registries that tell you what the actual raw IP address associated with anything in that domain is. Now, ultimately, there's a question of sort of what's the end of the line? Where is the information about what how domains are connected to internet addresses? Where is that ultimately stored? The world has, I think it's 13 root name servers, which are computers distributed around different parts of the world that contain sort of the ultimate records at any given time of what the association of domain names with internet addresses actually is. When you change one of those things, that change has to sort of propagate around the world and propagate to all these tables. It usually takes only 15 minutes or so, I think, these days to do that propagation. But that's sort of what happens if you changed that association between the domain name and the IP address. So another question is how do you route? How do you actually get to a particular IP address? And this is where things get quite complicated. And there's all these things, BGP routing and all kinds of other elaborate kinds of issues about sort of what is the best route to get from here to there? How does it change? What servers decide how the routes work and so on? And it gets even more complicated because in the end, your information is going to get routed through things like fiber optic cables that actually are the raw hardware that implements the internet. And different companies own different cables, and different companies kind of exchange information differently with other companies. And so it's like, well, I'm trying to get to this AT&T kind of network, I'm on some Verizon network. How does the Verizon network connect to the AT&T network? How does that all work? And ultimately, it's a pretty complicated system of all these routers and so on, and figuring out what is the fastest way for your data to get to the particular computer that you're trying to get it to is a complicated thing. And it's something which can change over time. It's something where there are different algorithms for figuring it out and so on. At any given time, you can find out how your computer is routing data to a given computer. There's a low-level command on Unix-like systems called traceroute, and you just type in traceroute and then the name of some domain or an IP address, and it'll show you all the hops that it's going through. So it'll say your data went from your computer to that computer that's down the street to that computer that's at your internet service provider. Your internet service provider then sends the data to some other computer, and eventually, if it's going across the Pacific Ocean or something, it'll send it to some computer that's connected to the fiber that goes across the Pacific Ocean, gets to the other side, goes to some other internet service provider, et cetera, et cetera, et cetera. And you'll typically see maybe 10 hops or something will be a not untypical thing to see. And each one of those hops takes a certain amount of time. So maybe the total time for your data to get from your computer to some computer on the other side of the world might be 200 milliseconds. And it's going through, that's a 2/10 of a second. It's going through a bunch of other computers, and each time it goes through another computer, it might take another 100th of a second or something to get transmitted, and so on. So that's kind of how the low-level part of the internet works. Now the question is, how does, for example, a website work? Well, when you go to a website, what's happening is you type in wolfram.com. Your web browser is going to send needs to send a request to the computer that is serving the website that is wolfram.com. Okay, so essentially what's happening in this HTTP protocol, that's the thing that is used for websites, what's happening is your web browser is basically saying to the computer that is hosting the website, it says, I want a page of the website. And the computer that's hosting the website then responds and says, okay, here's a bunch of data that represents that website. So what's happening is your web browser is sending a request. Usually it might be a so-called GET request that is a request. It's a bunch of data. You can actually see them there. They're just text. And it'll just say, get this page and so on. And it will send that data over the internet to the address that it got by translating the name www.wolfram.com or something to an IP address. It'll send it to that IP address. Okay, what happens when it gets to that IP address? Well, at that IP address, there's a computer whose whose main function is to just watch for requests coming in. And every time it sees a request coming in that says, get web page such and such, it'll say, okay, here it is. So that computer will see a stream of those requests. So to a big website, there might be thousands, tens of thousands of those requests every second that are coming in, where web browsers from all over the world are saying, I want this web page, I want that web page, I want that web page. And then that web server is responding by saying, okay, here's the data associated with that web page. Your web browser then receives that data and then renders it, and that's the web page that you see. Now, again, things get even more complicated, because when you say, I want to get the web page, I don't know, I want to go to wolframalpha.com, okay? Turns out there's more than one computer that can that can give you the data of wolframalpha.com. There are multiple, they're usually called colos, colocation facilities. There are multiple colos that contain computers that can give you wolframalpha.com. So when you actually send that request out, something has to decide which of those computers you're actually going to go to. Ultimately, it has to go from the wolframalpha.com domain name to an IP address. Each of those computers in the end will have an IP address. There's a bunch of tricky stuff. There's an idea called GeoDNS, which is something where you're actually looking at what is the geolocation of the computer that the request is coming from, and make sure you're sending the request to the sort of geographically or at least internet closest colo, so that the data can come back as quickly as possible. Now, again, something else that happens, it's again kind of complicated, is usually when you request a web page, you're just saying, I want the web page from such and such a company, and it has some web server and so on, and your request will have to go all the way to that company to get the data back. But actually, that's not the most efficient thing to do, because assume that data doesn't really change much or doesn't change at all, and assume many, many people request it. Then it makes more sense to store versions of that data closer to people's computers, not all the way at whatever company originally was making that website. So there are all kinds of networks, content delivery networks and so on, that that provide large numbers of computers, tens of thousands of computers around the world, that will store copies of sort of web pages, fragments of web pages, things like that, images, movies, things of that kind. And those are, that's often when you request one of these things, you won't get the data all the way from the original web server that was sort of the original producer of that data. It will instead be one of these caching servers that is that's easier for your computer to get to and faster for you to get to. So, I mean, there's even vastly more complexity than this to the whole way that the internet works. It's sort of remarkable sometimes that the system does work as comparatively well as it does. People, maybe a decade or two ago, people were very concerned about the idea of things like internet storms, where somehow all of the different routing of packets and data and so on would all get confused, like that incident I mentioned about the computer in Hawaii that said it took a negative time to route data through it, but other things that would just be a consequence of the dynamics of data routing around the internet. That somehow there would be these moments when the internet would dramatically slow down just because of some dynamics of the way that all this routing of data works. That has become less of a problem, it seems, over time, possibly just because the communication links on the internet have gotten faster, the router computers have gotten faster, and so on, or possibly because, and this is something that gradually evolves, the actual protocol for deciding which route you take on the internet. Although, as I said, that's a little bit of black magic that typically goes into deciding those kinds of things. And typically the different internet service providers and so on, and different setups for how you're connected to the internet will have different detailed ways that that's treated. So, okay, that was a very rough description of sort of how the internet and the web work and fit together. All right, very different questions here. Let's see. Question from Desideri. Is there a philosopher who developed a system which is close to my perspective right now? You know, I'm embarrassed to say I don't really know. It's hard enough to understand what kind of scientists conclude and say about things. But usually when you have a science theory, you can kind of boil it down to, and it's this particular thing, it's a particular idea. With philosophers, I think it's less plausible that one can boil things down to sort of one particular idea. It tends to be a whole kind of framework for thinking about things. And also, you know, when you look at science, for example, it's a question, do I understand this framework? Well, if I can write a program that implements the framework and I can kind of compute things from it, then I feel like I more or less understand the framework. With philosophers, it's like, do I understand what you know, Immanuel Kant had to say about this or that thing? I don't know. I could talk to somebody about it. They'd tell me, well, you haven't got it quite right. You try and actually read it. It's like, well, what does this sentence mean? I don't really quite know. There isn't sort of this translation to kind of computational language that's possible in more sort of direct science kinds of things. I mean, a good case in point is Gottfried Leibniz, philosopher who lived in the late 1600s, who I've studied a certain amount, and who, for example, was very interested in many of the kinds of questions that I've been interested in about things like, is there a sort of, he talked about a characteristica universalis, a universal language for describing things in the world, a philosophical language, as it was sometimes called back then, a way of sort of turning into what we would now, sort of a symbolic representation of things in the world that had some kind of precise, in a sense, mathematical character. It's very much the same kind of thing that I've spent many decades trying to do with our computational language, to find a way to represent sort of in a precise computational form things in the world. Anyway, Gottfried Leibniz wanted to do that. He made quite a bit of progress doing that. He also did things like, he was one of the inventors of calculus, and he also thought a bunch about mathematical notation. And he also talked about things called monads. And he had this whole theory of monadology. And I regularly get email from people saying, I think your theory is related to monadology. And, you know, I've wondered this for years, but I just don't really know. Because I can look at what Leibniz wrote, and I have done so, and I find it incomprehensible. Now, you know, it was written in Latin. I can just about probably pick my way through his Latin, but I'm usually reading a translation. So that's, you know, step number one away. But more important, the way people talked about things and the way people thought about things in the 1600s is really different from the way we talk about them today. I mean, he wasn't talking about, oh, we can turn everything into a symbolic language where we can compute this or that. He didn't have this notion of, this general idea of computation. He did have the idea that you could make, in fact, he himself spent many years building kind of a mechanical computer that computed things like addition and subtraction and multiplication and so on. But he didn't have the modern conception of computation. He didn't have all of the sort of modern framework of ideas that we have now. So it's really super difficult to translate from the way that I think about things today to what he was talking about and to figure out, was he really saying this? Wasn't he saying this? I don't know. I think that the same, as you get closer to the present day, it becomes a little bit easier potentially to understand what philosophers have written. But I have to say, for me, it's very difficult to know whether I really kind of nailed down, this is what the person really meant when they said this. It doesn't mean that the ideas aren't interesting and that it isn't worth reading what they said. And often, and I think it's a characteristic of philosophers, it's more the questions you ask necessarily than the answers you get that are what's important. I mean, it so happens my mother was a philosophy professor in Oxford, and so I would run into, at a time actually when Oxford was sort of the kind of world center for philosophy. And so when I was a kid, I would run into all these philosophers and so on. And sometimes I would sort of try and debate them on topics of science. I'm sure it was quite entertaining. I was when I was like 10 years old or younger and so on. I know from my own experiences with modern 10-year-olds and so on, that it can be really interesting to have those kinds of discussions. But in any case, I think one of the things I always used to kind of give the kind of philosophy profession a hard time about is, look, you're still talking about what Plato said. You haven't answered, and that was 2,000 years ago, and you don't have answers. You're still just debating. Was he right when he said this? Wasn't he right when he said this? This is a subject where you've been having discussions for 2,000 years. It's like, come on, let's get actual conclusions. And, in a sense, science has mostly been very different from that. Science has had this notion of progressive conclusions and progressive sort of layers of progress being made. Now, sort of the interesting thing with philosophy today is that some of the things that have been matters of philosophy and ethics and other places, they actually have to turn into actual pieces of computer code implementing, ethics for artificial intelligence or something like this. So all of those discussions that philosophers might have had for 2,000 years, you got to come up with some answer, because in the end, that self-driving car has to make an ethics decision, and it can't go back and consult Spinoza's ethics, treatise and have a debate about it. It's got, 5 milliseconds to decide whether to do this or that. And in the end, you've got to sort of turn philosophy into a code. And that's a process that is it's a very interesting process. That's sort of a thing that needs to be thought about today. And I think it's a general feature of philosophy that it's provided these sort of frameworks for thinking about things. And then at some moment, something, maybe it's science, maybe it's law, maybe it's something else, has to take that framework and do something definite with it. The existence of that philosophical framework is very important. But in the end, somebody's got to take it and make a definite decision on the basis of it. And I think we're about to see that happen for lots of other areas of philosophy. I mean, I know if you look at different areas of philosophy, things like epistemology, the theory of knowledge, ontology, the sort of theory of what exists in the world and so on, and or something like ethics, all of these things have very sort of concrete character when it comes to what we have to do in computation. I mean, for example, in a lot of what I've tried to do in computational language, a lot of the questions that have come up in linguistic philosophy, again, have to be answered with definiteness. A typical question in linguistic philosophy might be something like, what does it mean to refer to a thing? What is the sort of truth value of a statement? How do you deal with the possibility that the statement is about something that doesn't exist? The famous one that, at least in my mother's time, we were doing philosophy, was the statement, "The King of France is bald." Well, okay, if you're making that statement during the time of Louis XV or something, it could have a very definite, yes, it's true, no, it's not true, and so on. But if you're making that statement in 1965, the France didn't have a king in 1965, what does that statement mean? Is that statement a valid statement? Is it a statement? What is the truth value of that statement? Do all statements have to have truth values? What happens when the thing that's in the statement has nothing to refer to? Well, all of those questions are questions we concretely have to answer in Wolfram language. What does it actually do? And what does it do when you're referring to a thing where there isn't a referent of that thing? And there's definite answers. It treats it as a symbolic thing where it doesn't know what it is, and it has ways of dealing with that and so on. So these things which sort of were debating points in linguistic philosophy, for example, actually have to turn into the actual operation of a computational language. All right, let's see. Well, there's a question here about tips about writing essays. I write a fair amount. I write, I have my sort of writings blog-like thing. Right now, actually, last few days, I've been writing very much because I've been trying to write about these things called combinators that have their 100th anniversary on Monday. Tips about writing these things. Well, a tip that I should give myself is, it's always nicer if you can say things in less words, but it takes longer to write less for me. If there's something I'm trying to describe, if there's an idea I'm trying to describe, I can describe it kind of much as I would say it. But maybe there's a more minimal way to do it, which might take somebody less time to read. You can kind of go back and sort of try and squeeze it down to less words. I don't think I spend as much effort trying to do that as I might. I think one of the things that one notices, for me, when I'm writing, I usually, because I don't usually have that much time to write, I usually don't revise what I write very much at all. I usually get to the point where I think I know what I'm talking about, and then I write. And whatever I've written is pretty much what's going to be the thing that is the final form. I mean, I suppose one thing to say about writing in general is, the only way you're going to be able to write something reasonable is if you know what you're talking about. I think I used to always have a rule at our company about technical writing things like software documentation. I called it the zeroth rule of software documentation. The zeroth rule is, if you don't know what you're talking about when you write the documentation, then your readers don't stand a chance. So in other words, before you start to write, it's good to have collected your thoughts to the point where you kind of know what you're talking about, where you could explain them to somebody. And for me, I tend to write very much like I talk, I think, at least. And it tends to be, I find that a good way to sort of have a rhythm for what I'm writing. I think that let's see, I mean, over time, one develops, all kinds of ways to, I suppose one of the issues is, how do you say what you mean? People sometimes, particularly in the past, would have these writing styles, particularly in sort of more formal writing, where they would have very elaborate constructions and so on and so on and so on. And it's like, well, if you just ask the person, what do you mean by that? They would give you some 1 or 2 sentence description, and that would be great. But when they write it, it would turn into this 10-sentence, very elaborate, gnarly thing that's very hard for somebody to understand. I think it's a phenomenon, actually, in modern web writing, that people have gotten somewhat more direct. And the trick is, can you say something directly? How would you say it if you were just saying it to someone? And sometimes there are places where you might have some sort of analogy you would use, and that analogy is useful to put in your writing. I usually put it in double quotes and things when it's kind of not really the thing that describes what one's talking about, but it's kind of an analogy which is useful for understanding what one's talking about. I think that, well, let's see, what else can I say about writing essays. You know, I do lots of this writing, so I should have something to say about it. I think, you know, I tend to find, for me, that, you know, I kind of have to write in these blocks. And it's like, I write until I get to the end of a section, then I stop. If I kind of stop in the middle of a section, it's kind of bad news. Because when I come back and I reread what I wrote, I'm always like, well, I would say it a little bit differently today than I would have done yesterday. And it's very hard for me to kind of graft on the end for something that I had started writing. So it's good, at least for me, to write in chunks. Another thing that I found is surgery on writing is very dangerous and rarely works. That is, you wrote something and it's like, oh my gosh, I got to put this new piece of information into the thing I already wrote. But there's a definite flow to what you already wrote. And as you start saying, oh, but I've got to put this extra piece of information in, well, then this piece of what you wrote doesn't make sense anymore. You're pulling that thread, and then, well, then that thing doesn't make sense. And pretty soon you pull enough threads and the whole piece untangles completely. And that's, so, you know, surgery on writing is, in my experience, very difficult, which is why sort of getting everything sort of as organized in your thoughts as possible before you start to write is a good idea. Now, you know, I think in modern times, kids are taught to write, I don't know what they are, 5-paragraph essays and so on. And they're taught to have, you know, hooks at the beginning of essays and so on. To me, if you know, it's good to by the time you're writing an essay to a particular formal structure, kind of everything's over. You're not going to write a strong kind of flowing essay. It's going to be you know, something which is kind of seems very kind of wooden. And I find the same thing. I mean, a few times when I've written things, and when you revise it too many times, you end up with something that is where sort of the life that the prose had when you wrote it fairly quickly is completely removed, and it's turned into something which, yes, it's formally correct, but no, it's not really something that a human would care about. I mean, I think the worst case of essays written in human language is probably, you know, kids who write essays which are then going to be graded, where actually some of the grading is going to be done by a machine. And it's like, what are we doing here? You know, you write an essay, the essay is going to be read by a natural language processing machine, which is going to be trying to pull out various different features of what's going on and, you know, do the sentences parse correctly? Are the following, you know, words that might appear appearing? It's a, you know, to write an essay, for a human to write an essay that is to be read by a machine is, I think, a kind of a doomed proposition. But, you know, I think another thing that's important to say is I've been talking about essays that are purely in human language, in English or whatever else. Sort of the big future, and the thing that I'm very keen on, is computational essays, essays which are a mixture of being written in natural language, English or whatever, and computational language. I mean, you write an essay, you try and explain what you're talking about. There are different ways you can explain it. You can explain it in words. You can explain it with a picture. You can explain it in a computational language where you're describing where you're using computational language to describe the ideas you have. And kind of the concept of our whole Wolfram language thing has been to provide that kind of precise computational language that is a good way to talk about things that can be talked about computationally. That's a kind of a very clear way to organize and present computational ideas. And it's kind of, it provides something a little different than the sort of English narrative text. It's like, and then here's what we're actually talking about, and here it is in computational language. And then you can take that piece of computational language and just run it, and you do it inside the essay. And gosh, here's this picture, and now you can see the picture and understand something from it. And that's, I think, and sometimes it can be more than a picture. It can be some kind of interactive, dynamic, manipulable thing, you know, produced by some piece of Wolfram language code that's in one's essay. So I think that's kind of the, in a sense, to me, that's sort of the future of kind of essays about many kinds of things, is computational essays. essays that mix ordinary narrative text with computational language that gives sort of a precise specification of what's going on, and you can use then the computer to take that computational language and generate kind of content, pictures, whatever else, that immediately kind of makes your essay something that people can understand at a level beyond just reading the words and so on. So, and when it comes to writing computational essays, I think the main story there is to write your computer code as clearly as you write English language. There's an art to both things being clear. Can your computational language be nice and short? There are tricks that you can do that you can't do in English. You can iconize something. Let's say you're making a plot and you've got all kinds of details about this line should be green and that thing should be dotted and so on. That's not really important to the main communication of what that plot looks like. So in Wolfram language, in a notebook, you can just iconize that. You get a little blue blob that it just says, oh, there are a bunch of these options about how the plot's generated, but it's just a blue blob. If you ran that piece of computational language from your computational essay, that blue blob will be read by the computer as something that has all those options in it, or you can click it and see all those options. But in terms of the sort of communication of the computational language, you don't have to see those options. That's something you don't really get to do with natural language. Maybe you can have a footnote or something like that, but it's not really as elegant. This is a case where you get to really communicate clearly. And as I say, there's kind of an art to writing clear code, to writing code where it sort of explains what it's talking about, as well as just being able to actually execute for the computer what it's talking about. And typically, I would say in a computational essay, to reduce the visible pieces of computational language to maybe one or two, at most 2 lines long, is a good idea, whether by iconization or whether by breaking up the parts of some description that you're giving. I mean, it's kind of like if you're writing English and you write a sentence that goes on for a whole page. That philosopher, Immanuel Kant, who I was mentioning earlier, had a habit of doing that. By the time you have a sentence that goes on for a page, it's pretty difficult for humans to understand that. Same thing with a big lump of computational language that goes on for a long time. Unless it's sort of broken up in a structured way, it's hard for humans to understand that. So I think the, you know, when you're dealing with computational essays, one of the things that's great is, okay, one tip about computational essays. One thing that one might think about is, okay, I'm going to have in this computational essay, I'm going to have all these great visualizations. I'm going to show how in pictures what I'm talking about, et cetera, et cetera, et cetera. But let me first write everything, and then I'll go clean it up, and I'll put all those nice pictures in. Okay, big mistake. Because what happens is, and this happened to me many, many years ago, and I kind of made it a lifelong principle to not be caught by this again, which is, you know, you do that, and then at the end of your project, you're making all these nice pictures. Then you say, okay, let me generate all these pictures. Okay, you generate them. You look at them, you say, oh, now I understand what's going on. I wish I generated these pictures before. Well, you should have done. You should generate them early in the project so that you get to have all the advantages that you hope your final readers will have when they get to see those wonderful visualizations that you're making. Now, in practice, things don't necessarily work that way, because in practice, you may be kind of waiting to finish some elaborate way of arranging labels in a perfect fashion to label some plots and so on, and that might not get done until you're later in the project. But at least it's a good thing to aim for, to sort of have as much up front as possible in terms of the way that you'll present things. And I would say that in terms of you know, in general, the idea that I'll do a project and then I'll explain how to present it, I think is a mistake. I think that knowing how to present something is an integral part of doing a clear piece of work. And, you know, if there's a thing where one is, you know, it's not sort of an add-on at the end. Now, sometimes after you've done the piece of work and you've really understood it, you get to find a simpler way to explain it than you would have had earlier on. But I think even from sort of an early phase of a project, it's worthwhile to think, how would you explain this? Maybe you'd even start writing some kind of description of it. Depends on your kind of workflow, whether that actually makes sense. But early in the project, so that you can know that you know what you're talking about. I mean, again, one of the things that's great about computational essays, and in a sense, when I do projects, what I'm generating as I do the project, is endless notebooks, hundreds and hundreds perhaps of notebooks, each essentially computational essays. And those notebooks, if I'm working really quickly, they'll probably have very little English text in them, mostly computational language, which I can read perfectly well. But those notebooks represent kind of the thought process. And I'm always going back to old notebooks that I had, that I wrote long ago. In fact, I was just looking, even yesterday, at notebooks that I wrote in 1992, which I'm happy to say, because we've managed to keep compatibility in the Wolfram language over all those years. They run just fine. The only thing that's really weird about those notebooks, I bring them up on my great big computer screen now, and they're tiny. They're like, I had no idea computer screens or notebooks were ever that narrow. They're like, gosh, how could you ever see anything in that short a space? But the computational language in them still runs. Okay. Oh, lots of other questions here. There's a question. Okay, there's a question from Amorita here. Why do the electron and proton have the same amount of charge? It's a good question. We don't yet know definitively what the answer to that is. One of the things that's observed in physics is that charge, electric charge, is quantized. It means it comes in definite multiples of a elementary unit. The electron has 1 unit, actually -1 unit of elementary charge. 1 unit of charge. It's equal to sort of the elementary charge. Confusingly, when quarks were discovered in the 1960s and sort of confirmed in the 1970s, quarks have 1/3 of a unit of charge, and that was something people got very confused about. But so far as we know, there's nothing with a smaller charge than 1/3 of an elementary charge, 1/3 the charge of the electron. Now we know to very high accuracy that the electron and proton have the same electric charge. If they didn't, then hydrogen atoms wouldn't be electrically neutral. A hydrogen atom that has a proton in it and an electron in it, those charges, the proton has +1, the electron has -1. If they weren't exactly plus and -1, then there would be then hydrogen atoms would have a net charge, and the universe would work very differently than it does. But why are those two things? Do they have precisely the same charge? We don't know for sure. I have some ideas based on our theory of physics. I have a guess that it's kind of something like the following. If you imagine that you're winding something around, and you're saying, I'm going to wind it around, you're winding a string around a pole or something, and you say, I'm going to wind it around, it's got to come back to where it started from. Well, you don't get to wind it, 3/4 of, the only way that you can have it come back to where it started from is to wind it a whole number of times. And so there's a much fancier version of that, homotopy, that shows up in mathematics. And I have a suspicion that the reason that the charges of particles like electrons and protons are exact integer multiples of each other has to do with the fact that those charges are associated with homotopy, associated with things like you can only wind an integer number of times and come back to where you started from. But the actual details of how that works is a lot more complicated than that. We have some very definite ideas about how that might work in these models that we have based on rewriting hypergraphs and so on, and this kind of structure in which one can have kind of a way of kind of tangling up these hypergraphs, and there are only a certain discrete set of possible tanglings that are conceivable if you want the tanglings a little bit like the winding this thing around a string around a pole or something, is that in order for these tanglings to sort of line up properly with themselves, they have to be an integer number of whole number of pieces. Now, actually, in physics, in traditional physics, there is one weird way that people have thought about explaining the quantization of charge. It's a slightly technical thing, and it has to do with things called magnetic monopoles. So when you have an electric charge, great. there's an electric charge, you can have a single electron that has an electric charge. Okay, when you have a magnet, a typical bar magnet has a north pole and a south pole. The magnetic field is this kind of line, this vector that goes, let's say, from the south to the north pole of the magnet. You say, well, why can't I saw one end of the magnet off and just have a north pole without having a south pole? Can I have a magnetic monopole? Well, if you saw the magnet in half, you'll still have a north pole and a south pole. The place where you sawed the magnet will be another south pole, so to speak. The magnet is only able to be set up with this both north pole and south pole, a dipole. So people have wondered whether there might be magnetic monopoles. In the standard theory of physics, there aren't magnetic monopoles, but if there was a magnetic monopole, even just one magnetic monopole in the whole universe, it would force charge to be quantized. And actually, the way it forces charge to be quantized is very much like this homotopy argument I was describing, that in order for there to be consistency in the way that electromagnetism works, it's necessary for electric charge to be quantized if magnetic monopoles exist. Now, obviously, people have looked for magnetic monopoles. Nobody's ever found one. Probably they don't exist in our universe, but if they did, as a matter of consistency, charge would have to be quantized. But other than that explanation, we don't know a reason why charge is quantized unless we're dealing with something like our theory of physics, where we can start to see sort of underneath what's happening in space and time and what's happening in quantum mechanics, and we can start to have sort of real explanations for things like the quantization of charge. And hopefully in the next few months, we will know a lot more about that. Kind of the buzz phrases have to do with local gauge invariance and gauge groups and the limiting of this sort of complicated hypergraphs, not just limiting to something like ordinary space, physical space, but also limiting to this internal symmetry space that's governed by, so just like you can ask about in space, whether you can kind of continuously move from one point to another, or whether space is more like a fluid like water, where there are sort of discrete molecules there, whether there are sort of discrete atoms of space. That's one question you can ask. Another question you can ask is, if you're rotating things around, are there a discrete set of rotations or a continuous set of rotations? You can ask that about ordinary space. You can also ask that about sort of internal features of in particle physics, for example, where there are these kind of internal constructs that behave a bit like sort of rotation in space, but they're not rotation in ordinary space. They're rotation in, for example, color space. In QCD, in the theory of quarks and gluons, there's this notion of color space. You can talk about rotations in color space. And there's a question of, are those continuous rotations or are they in discrete jumps? And the belief is that just as when you have a large number of sort of atoms of space, things behave as if you have sort of a continuous space. So similarly, when you have these very complicated hypergraphs, that it will be the case that these sort of internal rotations in, for example, color space will also behave continuously. In mathematical terms, that there'll be a limit. In the case of ordinary space, there's a limit to sort of a manifold that represents space. In the other case, it's a limit to a manifold that represents a Lie group, which is the kind of a description of a continuous group associated with things like color rotations. And that's kind of the thing we think is going to happen there. There's a question here from Joel asking, why can't magnetic monopoles exist? Well, we don't know if magnetic monopoles exist, but in the standard equations of electromagnetism, there's an equation. These were equations written down by James Clerk Maxwell in the 1870s, 1880s, and they are the standard equations of electromagnetism. There's one important equation. It says div B equals 0, and B stands for the magnetic field, and div is the divergence of the magnetic field. And what that means is the magnetic field, you can think of magnetic field as being a bunch of field lines. They say kind of if you had if you had a bunch of iron filings, they would sort of follow these field lines. If you have something which is following the magnetic field from the South Pole to the North Pole or something, you're following the field lines. Okay, so Maxwell's equation, div B equals 0, says there is never a divergence of magnetic field lines. There's never a place where it kind of looks like an idealized hedgehog, where all the lines come out of a point. There's another equation that says div E equals the electric charge. E is the electric field. It is the case that electric field can have this sort of hedgehog form where the electric field lines diverge from a point that has an electric charge at it. What you would have to have if you had a magnetic monopole is that similar divergence of magnetic field lines. The equations say it isn't there, but of course the equations are made up to describe how the physical world works. And so I'm not really telling you why there aren't magnetic monopoles. I'm just saying that with the standard equations of electromagnetism, which seem to work really well, there aren't magnetic monopoles. But beyond that, we don't know a good reason why magnetic monopoles shouldn't exist. They just aren't part of the standard theory. And once you have that theory, when you build it up into things like quantum electrodynamics, the quantum theory of photons and electrons and electromagnetism, that whole structure of quantum electrodynamics is built on the assumption that magnetic monopoles do not exist. So if magnetic monopoles suddenly do exist, you have to kind of redo the whole structure of quantum electrodynamics. Let's see. Well, there's a question here. Well, there's a question from Flymo, as well as thinking about the Sapir-Whorf hypothesis. Do you think about how humans might be thinking in the future, paradigms of thought in the future? Yeah, so one of the questions, it's a big one for somebody like me actually, is to what extent does the language that we are the language we use affect the way we think about things? And this has been a long argument. There's this thing called the Sapir-Whorf hypothesis from the 1940s, 1950s, which was kind of the hypothesis that the way one talks about things affects the way one thinks about things. Sometimes what one thinks about affects how one talks about or what one talks about. If you live in a different environment, you're going to be talking about different kinds of things. You know, if you live in a place where there's lots of snow, you'll probably have elaborate words for different kinds of snow. If you live in a place where there's never any snow, you might have one word for snow, but you're not going to go into the micro details of snow. If you and sometimes so there's things like that. But then there are questions like, okay, let's say words for colors. What words do we have for colors? We have a word for blue. We have a word for green. We might have a word for teal. We might have a few other words. What words do we have, and how do the words that we have for colors, how do they affect the way that we think about things like colors? And for example, it's a sort of famous claim that in things like ancient Greek, there wasn't really a word for, I think, blue. And so things that we would now say were blue were described as sort of greenish or whatever else in that language. How does that affect the way we think about things? We don't fully know the answer to that for human language. For computational languages, I think we much more know the answer. I've certainly seen it much more in practice. That, for example, with our Wolfram language, you know, I've taken it as a major responsibility in my life to design that language in such a way as to let people think about things in a clear way when it comes to thinking about things computationally. And I can really tell that when there's a concept that we put into the language as kind of a word in the language, that's a sort of anchor for thinking about things in a certain kind of way. And I know for myself, I think, oh, that's a fold list kind of operation. If I didn't have a word for it, I wouldn't think of it that way. I would think of it in terms of some underlying constituents, but I wouldn't sort of collect it together and think about it in that same way. And I think words provide an important way to sort of organize our thoughts, to decide kind of what we think about. I mean, it's the same thing as when, you know, there'll be a name for some field of science. And the very fact that there's a name for it allows a lot of things to be built on top. You know, then there can be an institute for science X, and there can be a this, and there can be a that, and people can talk about it. Names for things are important. Now, the question of how that will evolve going into the future, interesting question. There are things that, I mean, this sort of trend towards more levels of, you know, different, when something becomes popular, then there starts to be a word for it. And once there's a word for it, people can talk in terms of it and they can kind of build ideas on top of that. And that's a process that's been going on throughout the evolution of language. And that's a process we can expect to go on in the future. The interaction of that with computational language is kind of interesting because computational language is a designed language. And so it allows one to have sort of a better forcing function to kind of make progress in defining things one can think about. Now, there's a question, are there things that we just don't understand today because we don't have the right sort of way of thinking about them, the right language for describing them? Absolutely, yes. I mean, I can see in the progress of science and technology that I've done, when one didn't have sort of the right framework for thinking about and talking about things, even when the sort of the facts of the situation were right in front of one's nose, one didn't understand them until one had this sort of framework for thinking about things. And over time, we get new frameworks for thinking about things, and we can expect that more things will be able to be understood. I mean, I've been working just recently on these weird things called combinators. I can explain one thing about combinators that relates to language, and it's a very weird thing. So in ordinary language, we have nouns. We have things like, the dog was chasing the cat or something. Dog, cat, nouns. But then we also have pronouns. We say, like, I don't know, Jim said hello to Jane, and she was happy. Okay, well, the she is a pronoun that refers to the noun Jane. And actually, because of the way gender works in English, we kind of, with that sentence, John said hello to Jane or something. We have these two different pronouns, and at least in the current version of English, we can distinguish those two different possible subjects that are pronouns by the gender of those pronouns. In other languages, it works differently. Sometimes there aren't genders of pronouns. Sometimes there are more pronouns, and so on. But the main point is that we can use pronouns to refer to things without having specific nouns that say what those things are. But there's a question of, okay, do we really, when do we need to name the things we're talking about? So for example, if I say, Jim was talking to Bill, who was talking to this person, who was talking to that person, I couldn't really say he to refer to something there, because the he can only refer to one thing, and there's lots of different he's in that sentence. And so how do we disambiguate that? Well, in computational language or in mathematics, we would say, call Bill X and Jim Y, and then we can refer to X and Y, and we're all good. The question is, do we really need that? Do we really need those variables or not? Or can we have sort of an elaborate system of pronouns that sort of says, well, this refers to that because in the structure, this is in that place and so on? Well, the answer is that 100 years ago, a chap called Moses Schoenfinkel figured out how you can do that in complete generality, how you can avoid ever having to name things, how you can always just describe things, and he did it in the context of mathematical logic, how you can kind of describe things just by how things relate to things without ever having to give a name to anything. So what he did is very interesting. It was very important for theoretical purposes. A lot of things were built on top of it. Knowing that it was in principle possible was very important. But if you actually try and use it, it's absolutely incomprehensible to humans, at least to me, and I think to pretty much everybody else. I mean, it's kind of sort of a famous thing that combinators and combinatory logic are something, well, you can in principle do things with combinators, but you'd never want to because they're just utterly obscure. They're really very non-human in the way that they work. You have these big complicated expressions of S's and K's, and they represent, oh, this thing goes there and that thing goes there, and they untangle in this way, and they run a bunch of steps, and you can see them untangling, and it's really cool, but absolutely incomprehensible. So that's an interesting example of something where it's kind of the idea of these combinators is sort of a world without nouns, that you never have to name anything. And can we humans deal with such a world? I don't know. Over the last 100 years, we've complete failure. People haven't dealt with that. People don't understand that. Is it the case, could it be the case, if we really cared, that we would sort of gradually build out a sort of conceptual framework where people would say, oh yeah, it's obvious how that works. Kind of an analogous thing is the following, that when we have, sentence structure, our sentences tend to be linear sequences. This is a sentence about meaning or something. it's a linear sequence of words, and we can kind of break it down into a tree where we're saying, you know, noun, verb, noun, things like that, and that's sort of a tree where we can say that's maybe the noun is broken into an adjective and a noun, and the verb has an adverb and a this and a that and so on, and it's kind of this tree of different structures that make up our sentence. And our brains are pretty good at taking that sequence of things in and sort of, you know, understanding, parsing them into that tree and seeing what it means. You know, we lose it if, for example, the tree goes too deep. So we say, you know, the cat which chased the mouse, which chased the fish, which chased the whatever, which chased the whatever, whatever, whatever. After we've gone sufficiently many levels deep, usually more than about 5, it's really hard for a human to understand what was going on. And, you know, when you pop back up to the top again, and then you say, and it was happy or something, it's like, what did you say? Hard to understand. So we have some practical limitations like that. But the question is the structure of, you know, sentences broken down hierarchically like this, which is, by the way, also the way that computational language breaks down its way of presenting things, same kind of hierarchical setup. Is that an intrinsic thing that we kind of have to have for the way our brains work? An example of how that wouldn't be the way things work is if you've got this whole network of this connects to this and that connects to that. And it's not a story of this thing followed by this thing, followed by this thing, followed by that thing inside that thing, inside that thing, like in a hierarchy. It's more just everything's connected. Things are connected in this whole network of items. And that's, by the way, more how combinators work for these purposes. And the fact is, it's pretty hard for people to understand that. It's kind of like you have something and it's a bunch of wires connecting things together. The wires aren't organized, it's just this big nest of wires. It's like, what's going on here? It's hard for people to understand that. You know, I've done a bunch of experiments on computational languages trying to see whether one can make use of the essentially visual input of having this sort of collection of wires, this sort of, this connects to this and this and this and this and this, rather than some kind of linear sequence. And so far, over the last, I don't know, 40 years or so, I've been trying to do these things. So far, all of those have been kind of failures. I actually have a new idea. So it's possible that there's a new direction there. But, you know, there's really a question of can we humans sort of build our cognitive apparatus in the direction where we understand things like that? Or is there something that really pretty much cuts us off from that? Are there stepping stones we can go to get there that, you know, in another, you know, some number of years, it'll be like everybody understands that? I mean, an example of something that might be thought to be difficult to understand is the way hyperlinks work, the way you're linking. It's like a graph. You go from here to here to here to here to here. If you explain that abstractly without the concrete instance of hyperlinks, it might be hard to understand. But people don't get that confused by hyperlinks and this idea that you know, you can link from one page to another and so on and so on and so on. So, you know, I think that particularly as some of these concepts get embedded in things that are sort of everyday, I think it becomes easier to understand them. I mean, for example, one thing in thinking about physics, quantum mechanics has always been an area that's hard to understand. As from our theory of physics, we're realizing that the underlying formalism of quantum mechanics is deeply related to the underlying formalism of many other kinds of things, like distributed computing, like the way that you can have large networks of computers doing things and so on. It's also potentially related to a way that one can think about kind of ways to build sort of financial systems with blockchains and things like this. Well, if it turns out we can use the formalism that comes from our physics project that is deeply related to quantum mechanics to make this kind of distributed blockchain for doing financial transactions, well, it'll be a fun thing in itself, but also it will mean that when people use that routinely, they will end up having an intuitive sense of the way things work in quantum mechanics, of things like, oh, you can't make these two measurements simultaneously, and there's this uncertainty, and et cetera, et cetera, et cetera. Those will be things where people, instead of those being weird physics effects that have to be explained to one, there'll be things that people say, oh yeah, I understand that because I'm used to that, because that's the way my financial transactions work, and so on. Let's see. Okay, I'm going to have to wrap up soon because I need to get back to my own writing effort here. Let's see. People ask these questions about, do I have an opinion about such and such a paper and so on. Those are super difficult questions to answer. I do a certain amount of work on history of science, and that requires me really digging deeply into particular historical papers. It takes a lot of work to really know what people said and what they were thinking and so on. And it's usually when there's a sort of a live human who wrote something, my general approach is just ask the person. It doesn't, it's hard to be sure that one is correctly representing what they're talking about. Let's see. Super skeptical asks the simple question of me, how are you? That varies from day to day, but right now I'm in major crunch mode, trying to finish some things that I'm hoping to do for the centenary of combinators. But it's a lot of fun. It's very interesting. Both the technical side of it and the historical side of it are very interesting, and I love doing things that like that. And I would say that a funny thing that's happened in my life, I guess, is I've been working on a bunch of different sort of major directions for a great many years, whether it's about computational language, whether it's about understanding the fundamental theory of physics, whether it's about understanding the sort of implications of computation, the sort of computational universe of programs, all these kinds of things. There are all these different sort of threads that I've been working on for a long time, and building a lot of kind of tools and understanding in these different areas. One of the things that's happened in recent times is that a lot of things are really sort of coming to fruition, things that I've been sort of building for a long time. It's like, yes, now we've got a finished version. Now we've got something that works from this. I mean, a big place where that's happened is in this fundamental theory of physics, where I'd sort of built a lot of tools and ideas, and then suddenly in the last year, they've all come together. And actually that particular phenomenon of those things all coming together after so many years of sort of having them be vaguely being thought about and making slow progress and so on is very encouraging to me to say, okay, let me take the other 5 projects that I really want to do and let's see if I can actually do them. And there are several that actually are really up on the, are hitting the front burner, I suppose. One of them is this idea of symbolic discourse language, the notion of being able to express not just the kinds of things we've expressed so far in computational language, but a lot more kind of everyday kind of things that we would express in natural language, being able to express that in a symbolic computational form. That's something I've been thinking about for a long time. I think finally I'm going to make a serious assault on that. It's a project that got started, not by me, obviously, in the 1600s, by people like Leibniz and Wilkins and other kinds of people building philosophical languages, but people kind of gave up since then. They just thought it was too difficult or whatever. We're now in a position, and I think I'm probably now in a position from having spent the last 40 years thinking about computational language design, I'm now in a position to actually do this. And so that's a project that I want to do. And there are other projects, like one that I've been sort of thinking about for a really long time, is how to make molecular scale computers, how to compute and build things sort of to order on a molecular scale. And that's something, in a sense, biology, we are the only successful example so far of molecular scale computing. What we do is, the way we work, so to speak, is to have all these molecules inside us that sort of operate to get things done, to make life happen, so to speak. In our when we build computers, we're building them at a scale very, very, very much bigger than individual molecules. And the question is, can we make something which is sort of a computational system that works at a molecular scale, and maybe a system that can actually just construct molecules, sort of construct to order a molecule that's this weird shape or that weird shape, rather than having to go through the sort of standard mechanisms of chemistry to get there. And I recently realized that a bunch of things I've done to do with our physics project, to do with even this project about combinators. Yes, there is a way forward. I think I know how to do this. And not only that, there's a company we've been working with for a long time that's built a lot of technology using our technology stack to make a big automated lab and I think that we might actually be able to really do this and actually do, in a sense, molecular scale computing and have sort of a way of compiling down to molecules. In a sense, that will be an exciting thing because, like, biology is our only example. This is kind of biology 2.0 of a different way to do molecular scale computing. I think that perhaps all the things have lined up so that it's actually now the time to do that. And the existence of this automated lab, which is programmable with Wolfram language, is for me is an important piece of that, because otherwise it's like me with test tubes and actually doing a physical experiments with molecules and so on it's not something I know much about, and it's not something that it would probably take me years to kind of develop sort of the skills necessary to do that effectively. But it looks like we're just going to be able to do that by typing Wolfram language scripts rather than having to actually move the test tubes around yourself, get the robots to do it for you, so to speak. So, and there are, well, I have a series of these projects, probably about 5 of them, which I'm now very enthused about really being able to do. I have to say that another direction that I find interesting is kind of explaining things and exposition of things. That's why I'm doing these live streams and so on. And I'm trying to figure out what the best way to take my interest in that and the things that I know and sort of find the best delivery mechanism for that to the world that is both I find fulfilling and is useful. And so that's another challenge. But yeah, the basic answer to how am I'm doing very well these days. Although my things are very, very busy, because it's such a strange thing that there are these projects that I've been working on for decades that are all sort of coming to fruition. Even a lot of stuff to do with the actual deployment of Wolfram language in the world at large. Lots of things happening there, very practical kinds of things, but things which I've yes, I've intended this to happen for 20 years, now it's actually happening. Okay, there's things for me to actually do associated with those things happening. And so that tends to generate just a lot of stuff to do, but it's really interesting. And I suppose that for me, the challenge is, do I get to do things that I think are worth me doing, or am I doing things where somehow it's like, why am I doing this? Well, a very large fraction of the time, I'm getting to do things where I say, this is a good use of my time. This is something that is both fulfilling to me and builds something interesting and is kind of something where people in the world at large get benefit from it. So that's pretty nice. All right, I should really wrap very soon here. There's a question here. Would you advise today's Generation Z folk to become independent researchers rather than academics? Boy. Academia is a good framework for doing all kinds of things. If you want to research some weird thing, you don't know what it's good for, but it's interesting, there's a decent chance you'll get to do that in academia. It's not a perfect chance, because academia has its own structure where it's like, oh, you've got to get funding for that. Oh, does it fit into physics, or does it fit into computer science or chemistry or things that get funding and so on. So it's not a perfect version of that, but there's a lot that you can do in sort of research and academia where you don't immediately have to say, and now I know how that's going to turn into a product, for example. I think that for me, the dynamics of companies and things like that work, in the way that at least I built a company, work very well. But that's because I've kind of managed to find a niche where the things that I find intellectually interesting are really very well aligned with the things that we can actually deliver as products. When I have some idea about computational language, it can get put in Wolfram language, and it can turn into a product that people get and that runs on all kinds of computers and in all kinds of organizations around the world. And it's something that's immediately useful to people. I have kind of a matrix through which to put ideas that I have. When you're in academia, the main matrix through which you put ideas is writing academic papers. And if your ideas if you can get it to an academic paper, but you can't quite figure out how to get it into something that's kind of useful to the world and a product and things like that, then that's kind of the right option. But, it's a different thing. It's like you can do a project and it'll be good for a paper and terrible for a product. You can do a project and it's great for a product and not very good for a paper. In a paper, it's like, well, we did this and we did this one example and it worked great and here's the result. And it's like you look at that from the point of view of a product and you say, that's useless. Nobody's actually going to try that one example. People want to do all these different examples and all these different cases. And that one example, it's kind of cool, it's kind of interesting to read about, but it's not useful as a product. Similarly, when you're building a product, there are things where you say, well, people are going to give us all these different kinds of input if it's a software product. And we've got to be able to deal with all of them. We've got to have all these heuristics for dealing with these different cases and all these different things. And it's really kind of complicated. And it's intellectually perhaps quite interesting. But you say, let's write a paper about this. How are we going to write a paper? We could say, here's the code. Great, it's computational. I say that'd be fine. But if we're going to say, and this has 10 heuristics that are associated with, if it's this case, that case, the other case, it's like, that's not the kind of thing that will be interesting in an academic paper. That's the kind of thing that's very useful in a product, not interesting in an academic paper. It's an intellectually interesting thing, just as that one example for the academic paper is an intellectually interesting thing. But there's sort of different tracks. And I think that's the thing to recognize in the way that those things work. Now, one of the challenges is, being an independent researcher. Well, in the practicalities of the world, people have to make a living somehow. And it's great if you can make a living doing the thing that you really want to do. I think I'm really very lucky that I've managed to at least construct for myself a mechanism where I pretty much get to make a living from doing the things I like to do. There's a lot of work to building such a structure for oneself, and a lot of things that require skills that not everybody necessarily has. And so it's that's a not necessarily for everybody kind of thing. But so, one model of life is you make a living doing something, and then you have a thing you're really interested in doing that's different from the thing you make a living doing. Maybe you're interested in the thing you make a living doing, but you're also interested in something else that isn't something you could make a living doing. I mean, like, for example, I find doing these live streams interesting. Has nothing to do with the way I make a living. I just do this for fun. It's a hobby, so to speak. And that's a fine way to exist. I think when it comes to doing scientific research, there is also the possibility of just do it as a hobby. Unfortunately, many fewer people than one might think succeed in doing that. There are definitely people who do, and many who I know who do it quite successfully. But it's in these years, it's surprisingly unusual. 100 years ago, it was much more common. These days, it's less common. Now, perhaps one of the reasons for that is that in a sense, it's easier to do meaningful research when there's a matrix in which you're doing it. When you're writing academic papers, when you're building products, it's somehow easier to make concrete the research you're doing when you have an environment like that. And when you're an independent researcher, it's like, well, I don't really care about writing papers. I don't really care about making products. Okay, how do you make something out of your research? Now, actually, we've tried to provide some venues in the Wolfram community, in our Wolfram function repository, things like that, for people doing computational kinds of things. It's a venue for, it doesn't matter who you are, where you are, what environment you're embedded in, so to speak. This is a place where you can do an interesting piece of work and get it out there in the world and have it be a finished thing. Because, one of the things that's sort of deadly sometimes in research kinds of things is the never finished project. It's like, well, I'm working on this, but there's no end point. There's no, yes, I've got to this definite milestone in the project. And I think it's really useful to have that. And people can spend, unfortunately, people do spend, a lot of time doing sort of hobby projects where there aren't really those milestones, those endpoints, those actual pieces of stuff that get produced. And sometimes it can be that isn't a very healthy way to do it. And one of the problems that happens is when you have to, for example, explain what you're doing, then you have to start from the beginning. If you're going to do a good job explaining it, at least, you have to start from the beginning, explain the steps, get to where you're getting to. You kind of can't get away with not starting from the beginning. But if you're just thinking about something, you never have to explain it. You're just like, well, this is my hobby and I'm just doing it and I don't really have to explain it to anybody and so on. You don't necessarily have to go back and think about it from the beginning. And maybe you realize after you've been doing it for a decade, then somebody says, well, can you explain it? And you go back to the beginning and you say, oh my gosh, that wasn't really right. The thing I started from wasn't really right. Well, you would have discovered that a lot earlier if you'd kind of had this milestone that you're trying to hit of saying, I'm going to explain it now. So I think that's an important that's one thing that's sort of a danger of the pure independent researcher kind of thing. Now, there are different environments, between sort of academia, there's sort of academia where the product is papers, basically. There's companies like mine where the product is products. And there are some small set of kind of intermediate kind of research institutes where it's sort of something in between. Usually the product is some kind of report. Usually there's something concrete that's produced. I remember, when people have tried to set up sort of pure thinking institutes, doesn't typically work very well. I mean, I don't think we humans are built for that. I think if you say to somebody, okay, you're some age, just think for the rest of your life. Doesn't matter what you produce, just think. That's a very difficult thing to do. I certainly wouldn't be able to do that. I mean, I do a lot of thinking. I enjoy thinking very much and spend a large fraction of my time doing it. But for me, sort of thinking, the way the thinking becomes real is by actually producing things, by writing things down, by writing pieces of computational language, by explaining things to people, and so on and so on and so on. I think this idea of just sit and think is one that humans find really difficult. It's kind of like being, it's sort of very isolating kind of idea. And I've seen institutionally when people try and sort of set up, let's get a bunch of clever people and just have them think. Usually doesn't work very well. It's usually much better when there's a sort of concrete output that the people are trying to get. And sometimes people will say, oh, that concrete output is really mundane and boring, and people should just be thinking these higher thoughts. Turns out, people think in my experience, people think much better higher thoughts when there's a concrete output than when they're just sort of floating around. And even when that concrete output seems quite mundane, and this is certainly something I've seen a lot, even when it's like, we're going to solve this practical problem. It has to do with this sort of computational issue, this, that, and the other. And then when you really dig into it, you realize, actually, the reason people haven't solved this problem before is because there's this great big intellectual chasm there that has to be crossed. And that's really interesting. And although it came out of this kind of mundane question, the reason people didn't get the mundane question answered is because they had to figure out all this deeper intellectual stuff. And you're kind of driven to that by thinking about this mundane question. You never would have touched it. You never would have noticed it was there had you not had this entry through this seemingly quite mundane question. Let's see. All right, maybe one. I think I should go because I really need to go work on my efforts in combinators. There's one last question here, which I don't quite know the meaning of, which is from Memes of Destruction. It's, do you like turtles? That has me a bit floored. When I was a kid, I used to keep a certain collection of pets, usually for some reason reptiles and amphibians. I don't know quite why, but I had what in British English is called a terrapin, but I think in American it's called a turtle. It's a small little, very, very brightly pigmented little critter. I thought it was kind of cool. I'm not sure I would say anything profound about it. I'll say two other things about turtles. by way of sort of free association. There's a kind of a funny saying when people are talking about fundamental theories of physics. Turtles are a thing that commonly come up there, and I think the reason is I think it's Bertrand Russell, a well-known philosopher, not one of my great favorites, but who lived a long life in England. Must have died in the 1970s, I think. He was apparently, I think it was him, was apparently giving a talk somewhere, and a woman asks him, is talking about something about physics and fundamental theory of physics. I hope I have the right person. I hope it was Bertrand Russell, not Arthur Eddington, that tells the story, but I think it was Bertrand Russell. The woman apparently says to him, look, I don't know what your theory of physics is all about, but what's really going on in the universe is the world exists on the top of a giant turtle. And that's the way the world is constructed. There's a giant turtle there, and the Earth is somehow on the back of the giant turtle, and things like that. And it's like, and then the person giving the talk, Bertrand Russell, whoever it was, says to this woman, well, what's that turtle standing on top of? And she said, well, it's another turtle. And it says, well, what's that one standing on top of? And apparently this woman said, look, you just don't understand. It's turtles all the way down. And so that phrase, turtles all the way down, has become a little bit of a joke phrase to describe, theories of physics and, it's hypergraphs all the way down or whatever else. So that's kind of a turtle, an abuse of turtles. So then I see somebody sent a thing about zombie kid likes turtles on YouTube. Okay, this is the problem. I'm obviously I'm obviously out of my depth in modern popular culture, and I should learn all these memes. It's kind of a shame. I would have thought I was exposed enough through my own children and through interacting with kids. I do try and learn the memes, but I'm obviously not doing as good a job as I should be at that. In any case, I'll mention one more piece of turtleism. So there's a very early computer language that was intended for kids named Logo. It's kind of modern version of it is this thing called Scratch. And the idea of Logo, it originated in the 1960s with a guy called Seymour Papert at MIT. The idea was it was a language where it would all be about controlling a turtle on the screen. And you'd say, go forwards, go turn left, turn right, keep going, et cetera, et cetera, et cetera, and make all these kind of patterns and so on. And this was and so the question, and for example, the Logo language actually got, it's very interesting. Some countries like, I think the country of Costa Rica, for example, sort of taught it to all the kids at one point. And I think it's kind of interesting to trace the effect of kind of teaching a computer language, an early computer language, back in the 70s and 80s and so on, to a wide range of kids. What effect has it had and those kinds of things? I'm afraid it's not quite as dramatic as effect as one might hope. I think because sort of the distance between sort of controlling a turtle on the screen and doing serious kind of computational language kinds of things is fairly great. I mean, I would argue that it's the job of a language designer like me to make our computational language accessible to kids so that kids can kind of start using sort of the same computational language that the grown-ups, so to speak, can use early on, rather than having to kind of dumb down a sort of language for kids. But in any case, this language Logo was very innovative and in its time. And one question would be, why did Seymour Papert think about having a turtle running around on the screen? Well, the answer is there was a thing that was at the 1950, might get this wrong, 1955-ish World's Fair. And it was a man called Gray Walter. His first name I can't remember. Gray Walter was his last name. was doing kind of very early artificial intelligence. And his sort of demo object for the World's Fair was a thing that kind of ran around on the floor and would have sensors which said, oh, it ran into a wall, turn around, go backwards, kind of like a modern, robotic vacuum cleaner or something. But it would kind of run around on the floor and do these things. It had various kinds of touch sensors. I think it may have had some kind of light sensor as well. And in order to sort of make this, the form factor that this thing operated within was this bunch of electronics on wheels. And so Gray Walter ended up putting this kind of dome on top of it. And that dome became sort of looked like a turtle. So the thing was called the Gray Walter turtle. And actually, it was pretty famous. It was it had its appearance. It was on the cover of Time magazine, and it was this is the future. Artificial intelligence is almost here. It's 1955, it's kind of like it's going to be robots all the way down, so to speak. It's kind of an interesting case of how did it come to be that even though the Gray Walter turtle, which had perhaps I don't think it probably had transistors in it. It certainly didn't have vacuum tubes. Wouldn't have been able to power vacuum tubes. It was doing very simple things. The path from that to sort of the true robot is a long path. It's been a surprisingly long path. But in any case, the turtles, not all the way down for physics, but turtles as they've appeared in sort of the logo computer language, and now I think Scratch has this cat called Scratch, I think, which is the modernized version of the turtle. So that's kind of the story behind that. I think that I'm not sure, the challenge when Logo was new, kids had never seen computers, and the idea of a kid actually being able to do something on a computer was really a new idea. At this point, with computer games the way they are, seeing this turtle move around on the screen is hardly dramatic and exciting. It's just something that's changed over time. All right, I still don't know what Zombie Kid Likes Turtles is about. I need a summary of that, or I'll have to actually go watch this YouTube video. Oh, should I watch it? All right, well, I'll see what I can do here.
Back here live at the Waterfront Village with my friend, Jonathan just got an awesome face paint job. All right, you're great. Good times here at the...
I don't know what this is about. This seems hard for me to parse. So I lose that meme. I don't know what that meme is about. Well, that's nothing new, right? There are plenty of, it's always one of these things where I'm always struck by the fact that people are asking about how language affects the way one thinks about things. I think some of these memes are good examples of how one can end up in a situation where it's like, I don't know what you're talking about. That thing is sick. Okay, I thought I knew the meaning of the word sick, but I know now it has a new meaning, and that, but I have to be able to translate that. In what context can I translate in what way? In a sense, language, the big thing about language is it allows sort of people to communicate with other people. But by the time, when you develop these memes, which one group of people knows about, another group of people don't know about, that sort of is perhaps it's the beginning of a new piece of language, but it's also a way that people don't understand what other people are talking about. Same thing happens in fields of science where somebody will have jargon in one area, and sometimes the jargon in one area will collide with the jargon in another area. And you'll be talking about well, for example, we have this thing in our physics theory called branchial space in American perhaps, branch, like branches of a tree, branchial space. Well, it turns out that one of the good things about the word branchial is that it doesn't get tagged by spell correctors, even though they haven't heard about our theory of physics, because the word branchial also shows up as a type of bone in a fish. So this is a typical example of, one person's talking about branchial space in the physics project, another person's talking about it in fish anatomy, and you don't know what you end up talking about. And I think that somehow the thing that really gets to me, I suppose, is these word fashions that last such a short time. And you can kind of see that if you look in Wolfram language, we have some of these word frequency data things, and you'll see these particular words like the word groovy from the 1960s. Had this very short-lived period when it was a cool, groovy, whatever word. I think well, the question for an old fogey like me is how quickly do you learn these things, and then do you only learn them after they already went out of style? And I'm afraid I'm probably one of those people who often learns these things only after they've gone out of style. But so I haven't learnt what this particular meme is about. I suppose an interesting question is whether if you to what extent, gosh, I remember the chap who invented the term meme, a chap called Richard Dawkins. I remember, I don't think I've seen him since the 1970s, when he was just starting to think about things like that term meme. I'm not sure whether the thing he thought of as meme is really the thing that has turned into the memes that we talk about today. His idea was it's kind of just like genes in natural selection and biology sort of communicate attributes of an organism to successive generations. Memes communicate sort of fragments of thoughts to successive groups of people. Anyway, I think okay, so the summary of this YouTube video is the reporter in this video asks a kid a question and he says, "I like turtles," at the 10-second mark. Okay, I completely don't get this. Okay, that's good. I one of the things that is sort of interesting in my line of work, I suppose, is that it's I've learned a lot of things in my life, and the thing that is always notable is that every day I'm dealing with things that I don't know about. Every day it's like, oh my gosh, how does this work? I have to try to learn this. How does it, what's going on, et cetera, et cetera, et cetera. And I think I think a lot of people don't imagine that's the way that they imagine, okay, you go to school, you learn a bunch of stuff, and then you're set. You don't have to learn anymore. Certainly for me, that is not the way it's worked, and it's not the way that I like it to work. And for example, I've just recently, last few days, I've been trying to piece together some aspects of the history of mathematical logic. And I thought I understood that reasonably well. But I look at a bunch of papers and it's like, oh my gosh, I didn't realize this thing, that doesn't make sense. That couldn't possibly have come from this. How does that work, et cetera, et cetera, et cetera. What is this weird technical thing that I thought I understood, but I obviously don't understand it? What does it mean? And, I think it's it's really a very worthwhile thing to kind of, keep learning stuff. The other big question, which is important when you try to make decisions on the basis of things you learned, is, do I actually understand that? Do I know when I understand, or do I think I understand, but I don't really understand? And, in what I do for a living of computational language design, it's kind of important to know when you really understand, because if you're going to do something where you say, this is how our computational language is going to work, we've maintained compatibility now across a third of a century in our language. And so it's like, if we put something in today, we better not make a mistake, because we're going to be stuck with it forever. And so it's then rather important to know when you know what you're talking about. And I think something that I've learned over the years is, what does it feel like when I kind of know that I know what I'm talking about, versus what does it feel like when I'm still like a little bit uncertain of, I don't know what this is about. I don't know what's going on. Can you distinguish those two things? And, I think sometimes in the modern education system, people are rushing so much, write another essay, write another thing, do this test, do it to time, et cetera, et cetera, et cetera, that people don't get used to this feeling of, yes, I really understand. I really understand what's going on. There's real sort of, the foundations are on bedrock. And, whatever you tell me about this thing, if you tell me something different, I'm not going to be confused because I really understand this. And people don't always get to that point. And I think that's a really useful point to get to. And it's also really useful to know when you've got to that point. when you're still kind of floating around on sand, and where something could come along where it's like, oh, I don't understand that. That's important when you're trying to make these kind of intellectual or technical decisions of, should we really do it this way or that way? Well, I really understand. I'm really confident this way is going to work. Or I don't really understand. I'm not sure. I don't know whether it should be this way or that way. Let's try and find something where we don't have to commit to it being this way or that way. Okay, so someone's commenting about this mystery meme. That I get the meme because I'm laughing, that it makes no sense. Okay, wow, all right. Yeah, okay. Well, clearly more for me to learn. That's a good example of something that I know I don't understand. And it's a terrible thing. Sometimes when we are trying to find ways to, explain Wolfram Alpha for students or something, and it's like somebody will show me, this is sort of an ad we're going to run in the sidebar of Wolfram Alpha or something like that about what we're doing or whatever else. And I look at it and it's got this cool picture and so on. And I say, I'm always a sucker for these pictures that have weird animals and things in them and stuff like that. And things like, our spiky 3D logo with sun hats and stuff like this. I always think those are cute. I don't know what other people do. But it's a little bit, I kind of know it's like, this is something that is intended to communicate to people who are much younger than me and who understand all these memes and things. I don't understand this. Don't ask an old fogey like me about this question, because I have no idea whether people will think this is cool, campy, crazy, or incomprehensible. That's so people can comment on. We have a whole line of a designer in our art department. At some point, started designing these wolves that are kind of the wolfy symbol that get used for various kinds of things related to our products. Like there's one that for some reason I started calling the butler wolf, which is a wolf dressed up in a kind of tailcoat with a top hat and things. It's a kind of a welcoming wolf that appears on some of our kind of introductory documentation type stuff. So, it's a good question whether that, I think it's amusing. I think it's kind of cool, but I don't know whether other people do or not. Hard to tell. I mean, it's always when you're doing user interface design for computers these days, one of the things that people will sometimes say is, that's like Clippy. And that's not a term of respect. For people who don't remember or don't know this, this is from a while ago in Windows. There was this kind of helper icon that was this helpful paperclip with this kind of personified paperclip with eyes and things, and it would blink at you and all that kind of thing, and it would where the paperclip would come up and make a helpful comment, or what it thought was or its programmers thought was a helpful comment when you were using Windows, and people didn't like Clippy. They thought Clippy was they just hated Clippy. And I remember that I thought Clippy was cute. I didn't think it was particularly useful. It didn't really work quite well enough. It didn't quite have the right things to say at the right time, but I thought it was really cute. And I remember, for example, when you would print things, the printer version of Clippy was this kind of paperclip that was undulating like it was kind of going through a piece of paper going through a printer. I thought it was all really cute, but to prove that one doesn't necessarily know what other people are going to find cute or not, people generally hated Clippy. Possibly, as I say, because of the functionality rather than because of the graphic design. But when one's doing user interface design, and particularly when one's doing this kind of, let me assist you as a user, and providing this kind of, thing that is an assistive thing, a common kind of user interface comment is, make sure it isn't like Clippy. Well, our wolves aren't animated, so we're not like Clippy there. All right, I better wrap up before I say anything too silly, anything more silly. about these kinds of topics. So, all right, well, thanks for joining us, and look forward to seeing you on another live stream. Bye for now.